going to leave that down here. I have to record my lessons right now for somebody who was not in school for a little while. So if you ever miss a day, I'll have some videos of lessons online, just so you know. All right. Woohoo! I know, that's so much better for you, Seth. I need to start doing this all the time anyway. Radius and diameter. Those should not be new words to you. So who can raise their hand and give me radius in their own words? Like, define radius in your own words.
Miss Kelly,
Yes, Seth, go ahead.
isn't the radius half the circle?
That's true. I'd love something a little more specific than that. Nick?
The area of half the circle.
Like where from the outside of the circle to the center.
Okay, I'm just going to switch those around. But you're correct. So it's a segment. And you said it goes from the outside of the circle to the center. I'm just going to flip that around and say it's a segment that goes from the center to a point on the circle. And there are infinitely many, and radii is the plural word for radius, so I promise I'm not making up words up here. But there are infinitely many radii inside of a circle, and they're all the same length, so that should not be new information to you. They're all the same. It's like when we use a compass to make a circle, that length of the compass is the radius. And then the diameter, what's the difference between the radius and the diameter? I didn't understand that.
Full length.
The full length, yeah. So like a radius is half the diameter. So in other words, a diameter starts and stops on the circle, but it has to go through the center. So the way you're going to see it on the quiz is the diameter is a chord, meaning it starts and stops on the circle. It's a chord that goes through the center. So I said earlier that a chord doesn't have to go through the center, but it could. And when it does, it's called a diameter. Now, a diameter always cuts a circle in half. It always creates a semicircle. And then there are infinitely many diameters as well. So wherever you put that diameter is half your circle. And we'll get more into that when we get into spheres next chapter. I didn't even say, we have 2 chapters left. Woo, woo, woo. This chapter on circles, and then one more chapter on area and volume, which actually a lot of it's not new to you. You've learned it before. So we'll do some 3-dimensional shapes and 2-dimensional shapes.
When's the last test?
The last one, May, the final exam. But we only have 3 tests left. Chapter 11, Chapter 12, final. It's getting there. Okay. So in your journal, if you're a visual person and you didn't draw your own picture, there are some pictures in the journal. Because today, what we're going to focus on in this first quiz is it's just going to ask you, like, give me an example of a chord. Give me an example of a radius, so on and so forth, so that you're familiar with the vocab. All right, so our first problem here. Please go away. Oh, that's good. It says, tell whether the line ray or segment is best described as a radius, chord, diameter, secant, or tangent. So those are your 5 options. Now, something I didn't talk about yet that's important, because it's going to ask on your homework, is how do you name a circle? You name a circle by the center. So notice that they call this circle C. That's because the center point is called C. So if your center point was called M, and those of you, once again, texting underneath the desk, it's such a poor decision because this is new information for you. If it was a circle with a center point labeled C, you would call it circle M. If the center was called M, sorry, I think I said C. So you name a circle based on what the center point is, FYI. All right, let's go through this. It says your options are tangent, secant, diameter, chord, or radius. So segment AC, let's start there. Segment AC. Chris? That is correct. That would be an example of a radius. It goes from the center to a point on the outside of the circle, or to the edge of the circle, somebody said in another class. Segment AB.
Diameter.
Diameter is correct. Thank you, Seth. It's a diameter because it goes through the center. If it doesn't go through the center, it's not a diameter. Ray DE is the next one. Ray DE. Now, Seth, since you already answered, I'm going to ask you not to answer this one, okay? So, Ray DE on the outside of the circle. Caleb? That is an example of a tangent. Very good. The tangent, just as a hint to you, is the only one that's ever on the outside of the circle. And then line AE. Just making weird noises. Line AE. Now, it's a line, which already rules out some options, and it doesn't go through the center. So a line that goes through the circle and intersects in 2 points. Spencer? A secant is correct. Now again, pronunciation, secant. It's probably called secant, but I'm lazy, so I just say secant. And then I missed some on my sheet. So segment AG. Segment AG. Now, here's where people get really confused a lot. So segment AG, even though there are arrows on the end, they're not referring to the entire line. They're only referring to the segment A to G. So I know there's arrows here, but you have to kind of ignore those for a second. So segment AG, who can raise their hand and tell me what they think that one is? Melissa? That's going to be a chord. I know there are arrows on the end, but they're only talking about the little section of it, AG. And then C to B, somebody new again? What would we call C to B? Segment CB. Chris has already answered, although thank you. Tyler, you want to answer?
No.
Oh. Wait. Radius. Very good. That'd be an example of a radius. So this is like the first part of your worksheet right here, FYI. Now the last problem says, name a tangent, and then name a point of tangency. So I just want to clarify that the tangent's the line on the outside, and there are a lot of different ways to name that, because you can name it as a line, array, or a segment, first of all, and then you can use any of those points. So I could call it line DB, I could call it line DE, segment BE, ray BE. There's lots of different options. So I'm going to call it line DE, but that is not the only name for it. So on your homework tonight and tomorrow, when you name a tangent, you might not be wrong just because your answer doesn't look like the person next to you. Now the point of tangency, there's only one of. So who can erase? Oops, I just gave it to you, so never mind. The point of tangency is where the tangent touches the circle, which in this case is point B. I colored it and then almost said, tell me which one it is. Okay, questions so far? Pretty straightforward. Now again, the point of all this vocab is because this vocab is all going to come up this chapter, so you should probably know what we're talking about when it comes to it. Now this specific section is going to be all about tangents, just so you know. A little more vocab for you. This isn't necessarily the most important part of the section, but we are going to refer to some of these things. You don't need that top part, but you do have 3 different options for how circles could intersect. They could intersect in 2 points, they could intersect at 1 point, or they could not intersect at all. Those are your 3 different options. I guess technically there's a 4th option where they intersect at all the points, but we'll get to that later. So 2 more vocab terms here. We're almost done, I promise. Tangent circles, almost done with vocab. Your tangent circles are coplanar. We haven't heard that word in a while. Coplanar just means on the same plane. So coplanar circles that intersect in 1 point. Whoa, new color. And then concentric circles are coplanar circles that have a common center. So if you think about like a basic target, not like a dark target, that wouldn't really apply here, but a basic target that you would see somewhere has a bunch of concentric circles on it. They all have the same center, but they're different sizes. and we'll talk a little bit more about tangent circles. So the tangent circles, you have what are called common tangents. Last vocab term. I know your hand's tired. Last one. We're going to have two different types of common tangents. Write down those definitions, but then I'm going to put it in a little bit of simpler terms for you. Oh, if you want to wait, that's fine. I guess I can tell you right now. So it says the internal tangent joins the two centers, but basically a common tangent is a line or segment. You should write this down though. That is tangent to two different circles. So it's one line, but it's touching two different circles. If it's internal, it'll go through the middle of the circles. And if it's external, it'll be on the outside of the two circles. And so we'll draw some examples on your note sheet. So most of the vocabulary on your quiz comes from this section right here. And then just a few from a couple of other sections. It's a long chapter, by the way, too, 7 sections. I know, it's really long. But like, there's like one theme for each section, so they probably could have condensed it more. Okay, so if you look at this red picture, you have an example of an internal tangent that goes between the two circles, and then an external tangent that's on the outside of the two circles. And if you were to go with this definition, if I draw the centers of those two circles and connect them, that tangent goes through there, and that's what this definition is saying. It says if the tangent connects or goes through the line that connects the centers, then it's internal, and if it doesn't, then it's external. But basically, external will always be on the outside. So we're going to draw some examples here. And you have your 3 different scenarios. The scenario of these circles not touching whatsoever, the circles touching in one spot, and then the circles touching in 2 different spots. For the first example, if I were to draw an internal tangent, a common internal tangent, it would have to touch both circles and go between the 2 circles. So something like this. That would be an example of a common internal tangent. One line touches 2 different circles and it goes through the middle of them. A common external tangent would be one line that touches both circles but is on the outside of the 2 circles. So something like the blue one. Letter B, when the circles are touching, there's only one option for an internal tangent because there's only one line here that will touch both circles and also go through the middle. So that'd be an example of an internal tangent. And then the external would be on the outside. Now on your homework, it's going to give you the picture and then say, is this internal or external? Just so you know. So you won't have to draw it yourself. You'll just answer internal or external. Now, letter C would not have an internal tangent. There's no way to draw a line that touches both circles once and goes through the middle. The only way to draw a line that would go through the middle would be if it touches the circle in 2 spots. So this one only has external tangents. Like this would be one example, and this would be a second example, and there's probably more. But that one only has exterior. No interior. Now again, the importance of this is just understanding what they look like and being familiar with the vocabulary. We won't do a whole lot with those tangents. All right, so we have 2 main theorems here that we're going to talk about. The first one says, if you have, I'm going to my little file, if you have a circle and you have a tangent to that circle, and I can move this tangent anywhere I want. So you have a tangent to the circle, it's touching the circle in one spot on the outside. If you connect that tangent to the center, like to this radius, then it makes a 90-degree angle, okay? And I can move this wherever I want. And is it still a 90-degree angle? Yeah. Now, what do you call two lines that make a, and then it's fun to do that. What do you call two lines that make a 90-degree angle?
Perpendicular.
Thank you, Seth. Perpendicular. So our first theorem here says if you have a tangent, it's always going to be perpendicular to the radius that connects at the same point. So wherever your point of tangency is, if you connect that radius, that'll always be a 90-degree angle, always. Our second little theorem here involves two external tangents. So let me go to my second file. I have two external tangents here, one here and one here. And again, I can move them wherever I want. And when that happens, and it's possible they would never intersect, but usually they're going to intersect. And they intersect here at a point E. If I draw segments from the point where they intersect to each point of tangency, so E to D and E to C, I'm just going to take away the tangents for a second. What's true about them? They're what? They're equal length. Someone said isosceles. I got you, like your brain's in the right spot. Yeah, and I can move these tangents wherever I want, and those little lengths are always going to be the same. So I can move them, and those lengths will always be the same. Okay? So that's our second theorem. Our second theorem says, even though they don't show you the entire tangent, if you have two tangents that intersect, so pretend that they're going on forever. If you have two tangents that intersect at a point, from that point of intersection to each point of tangency, those two little segments are always going to be congruent no matter what. Congruent means same size, equal lengths, however you want to interpret that. So our first problem here says, is ST tangent to circle P? Yes or no? Well, if this is tangent, we just looked at that theorem that said it has to be perpendicular to that radius. It has to be, if it's tangent. So we're asking ourselves, are those lines perpendicular? If they're perpendicular, then they would create a little right triangle here. Back in chapter 9, section 1, what did we use to check and see if three numbers made a right triangle? Not SOHCAHTOA, but what came before that? What did we check to see if three lines made a right triangle, or three numbers made a right triangle? Section 1, last chapter. Emma? But square them. Pythagorean theorem is what I was looking for. I think you were kind of there, you just weren't squaring them. We're going to check Pythagorean theorem. If Pythagorean theorem works, then it has to be a right triangle, and thus those lines have to be perpendicular. What would your C be in this case? 37, the biggest number, and the hypotenuse across from the right angle. And then your 35 and 12 would be your A and your B. Now, I know you guys don't have calculators, all of you, so I'll go ahead and type some of these in. If you have a calculator, great. So 35 squared, big number, 1,225. 12 squared, we should know that one. 144. 37 squared is 1,369. So I'm not solving here. I'm asking, like, yes or no, are they equal? 1,225 plus 144 is 1,369. So did it work?
Yeah.
Yes. So it's kind of like a chain effect. Because this was true, because a squared plus b squared equals c squared, this has to be a right triangle, that has to be a right angle, those have to be perpendicular, and yes, ST would be tangent. So if Pythagorean theorem didn't work, then no, those would not be tangent. Now, this theorem works as an if and only if theorem, so it works two different ways. They can say, is it tangent? Or they can say, it is tangent, now find your radius. So on this one, it says B is a point of tangency. I'm telling you it's tangent, which means it is a right angle. B has to be a right angle. Find R. So again, we have a right triangle here, and we're going to use Pythagorean theorem one more time. But it probably looks a little bit different. Now let's talk about those R's. Since we're doing a chapter on circles, what do you think the R stands for? Radius. It's going to the rest of the chapter. R is going to stand for radius. So that's why they put them in red as well, just to show you it was part of it. Now, what's our A and our B here? Let's just start that. What are the two legs, the A and the B? 80 and 80 and R are our legs. 80 and R that make up the right angle. Now your C is your hypotenuse across from the right angle, which is all of this, A all the way to C. So your hypotenuse is not only 50, and it's not only R, it's all of it. So how do I write that as an expression? Too much. What? Not 50R, 50 plus R.
Would you square that?
No, well, we will in a second.
50 squared plus 1?
Just 50 plus R for right now. Like if I walked 50 feet, and then I walked whatever the radius is, more feet, I walked 50 plus R feet. Now, I understand where you're getting the squareds from, because now you're thinking, but it's C squared, and you're right. So we're going to take that 50 plus R, and we're going to square it, which should now be showing you what we did on Friday with the whole box method thing, which we'll review again. Now, I just want to point out, I could have called that R plus 50. Like 50 plus R and R plus 50 are the same expression, because addition order doesn't matter. All right, let's just take care of the left side. 80 squared. What's 8 squared? 64. So 80 squared is 6,400. And then something squared is something times itself. So 50 plus R squared is 50 plus R times 50 plus R. And this is on Friday where we practiced that box method. If you were gone Friday, we'll go ahead and do it real quick here. So this should look familiar to you. 50 plus R on one side, 50 plus R on the other. Now normally when you multiply binomials, it doesn't matter which one's on the top and which one's on the side, because you're multiplying nonetheless, so it doesn't matter. All right, now when we do our box method, we take the cross product of each row and column. So this first top left box is going to be the row 50 and the column 50. So what's 50 times 50? 2,500. What's 50 times R? 50R. Same thing here. 50 times R is 50R. R times R is R squared. So 50 plus R times 50 plus R, we just did over here, is 2,500. Don't forget to add your like terms that are typically in the diagonal together. So what's 50R plus 50R? 100R, and then plus R squared. Now, this looks like a lot, right? Like, how am I going to solve this equation? There's so much happening. But what's on both sides of the equation right now? R squared. So guess what? We get to take it away, which makes it a little bit nicer. So now we have 6,400 equals 2,500 plus 100R. Now it looks bad because they're big numbers, but that's just a simple two-step equation. Two-step equation. Minus the 2,500 over. 3,900 on the left, 100R on the right, divide by 100, and R equals 39. And we'll do another one of those in a second. And if you're doing it correctly, your radius should be a whole number. They're not going to give you a radius that's some weird decimal or fraction.
What would be doing those? Like radius or something? Radius.
Oh, no. Not on a problem like that. Okay, last little piece here before we do a few more review problems is, this is that second theorem. So the second theorem that we talked about said if you have two external tangents that intersect, then from that point of intersection to each point of tangency, those are congruent to each other. What can you do with two expressions that are congruent? Set them equal. We did so much trig and like complicated math last chapter that I bet this is kind of nice. Like, remember when we used to just set things equal and solve? Minus the 4, and we get 3x equals 24. Divide by 3 and x equals 8. Now you don't need to plug it in here because it just says find the value of x, which you did. So you would not need to plug that in. Okay, super quick little review here. Now, if you're like worried about work time, we're not learning anything new tomorrow. We're just gonna do a warm up and then maybe like have an exit ticket, maybe, but you'll have some work time tomorrow. So don't fret if you're freaking out about that. So quick little review here on those two theorems. The first one says, is DE tangent yes or no? So we're gonna check the Pythagorean theorem here. Yes or no, is a squared plus b squared equal to c squared? So is D a right angle? Now your A and your B are your 3 and your 4. Do you agree with that? 3 and the 4 are the legs. Now your C, let's talk about that. There's one on your worksheet like this, so this is a good one to look at. Your C is all of this, C to E. That length is not 2. 2 is only this little piece on the outside. And you don't need to call this X. This right here is a radius, and all radii are the same length. How long is your radius in that circle? 3. Which means this little radius is 3. So how long is your entire hypotenuse? 5. There's one on your homework like that. Just be on the lookout. 3 squared is 9, 4 squared is 16, 5 squared is 25. Is 9 plus 16 equal to 25? Yes. I'm going to go through 7 pretty quickly, so try and follow along as quick as you can. This one says ST is tangent, so that is a right angle, so we're going to use Pythagorean theorem here. This is what we just did. Now the hypotenuse, who can raise their hand and tell me what I can write as the hypotenuse here, like an expression that works for the hypotenuse. Okay. 18 plus r. R plus 18 works just as well. So for our Pythagorean theorem, we're going to have r squared plus 24 squared equals 18 plus r squared. R squared is just r squared, which will eventually go away. 24 squared is 576. 18 plus r squared. Here's 18r, here's 18r, here's r squared. 18 times 18 is 324. And that's just super quick box method. That's what I did up there. So 18 plus r squared. And I have a lot of people always distribute squares. You cannot distribute squares. It doesn't work that way, unfortunately. All right, so we got 324 plus, what's 18r plus 18r? 36r, somebody so quietly whispered, plus r squared. What cancels here again? The r squareds cancel, and we get 576, let me bring it up for those of you that can't see, equals 324 plus 36r. Even though it's big numbers, it's just a two-step equation. Minus 324 we get 252 equals 36R. Divide by 36. I'll go back. R equals 7. Okay. So I did Pythagorean theorem. The C was Q to T. So R plus 18 or 18 plus R. Yeah? When you square that, you have to box method it, which is what this was in green. Well, then the R squared canceled, and then it was a two-step equation. Hold on one second, guys. You got to see this real quick. Number 8, when you set those equal, you get two different answers. How do you undo a square? Square root. But when you square root numbers, square root of 9 is 3, but what goes in front? Plus or minus 3. The only reason why -3 is okay here, because normally we say you can't have negative lengths, is because x is not on its own. All right, so I really dropped the ball on homework and didn't enter it in time for a packet, but I copied all the sheets today, and you guys can staple your own packet. But for today, I just have an individual worksheet. I'm so sorry.
It's okay.
I just totally forgot about it until the end of last week.
It's all right. We don't make mistakes.
Thank you. Sorry about that.
Wow.
But like I said, they're all copied, so we'll make packets tomorrow. We'll include that in our day. So 10.1 worksheet will be your homework.